You said good morning. For me, it's good afternoon, but it's okay. So good morning for all of you, to all of you. I'm really sorry, but as I just explained to Dan, I had in the last 2 months two very serious accidents in my immediate family, and so I not only I'm participating remotely, but I have very little time during this week. So sorry for that, but family comes first. Um, okay, before I really go into the talk, I want to make some introductory remarks. Well, in some sense, Dan just mentioned my name as a founder of Minfield Games, and I disagree. I disagree because I think that Minfield Games existed before they were named, and they existed in economics. In heterogeneous agent models, Hayagari, Yoget, etc. In other contexts, I'm thinking of the Weissman-Price model, and of course the Krussell-Smith model, which certainly was very influential in what we attempted to do. Not being a fan of Bruno Latour's thesis in sociology, which considers that things do not exist until they are named. That's why I slightly disagree with the term founder, but that's irrelevant. More relevant is the fact that indeed with Jean-Michel Lasry, we coined the word Minfield Games. And that's the second time it was catchy enough, but I believe now it's inaccurate, because I believe that games are just a marginal accident in the whole field. I'll come back to that later on. Anyway, the terminology is there. Right from the beginning, I knew that one could write. I did so very early on in my lectures, infinite dimensional equations, which are known nowadays as the master equation. But I was very reluctant to go into that direction because precisely of the infinite dimensional character and the difficulty to compute, etc., the analytical difficulties, and so on. But the interaction with Bob Lucas, again in economics, who mentioned Krussell-Smith's paper, showed us that we had no choice. We had to go there. So why I'm a little bit reluctant about the use of the word games in Minfield Games, it's because I don't think it's really what we can achieve in terms of modeling of large populations. Basically, what we are concerned with are dynamical equilibria for large populations. Each member of the population, a generic member, assuming to simplify that there is only one population, makes choices, decisions, adopts a strategy, which doesn't come necessarily from an optimization principle. Think of bounded rationality, worst case scenario, and so on. So then the notion of Nash equilibrium and games completely disappears in such a context. So first observation on the choices being made, which can be elaborate, involving lots of anticipation, or which can be more agent-based like. They can still be nonlinear depending on the evaluation function or value function. But there are many, many possible options. And then these actions, all those individual actions, have an influence on the evolution, on the dynamics of the population. But it doesn't need to be the only influence. So once again, this changes a little bit the picture. And why I'm insisting upon that is that because we have been accumulated in real life applications more and more examples who fall out of the scope of games. Also, let me emphasize the fact that there were two examples in our original papers which were not games and were still dynamical equilibria for large populations. Well, anyway, so if we think large population, we have to define the state and dynamics of a large population. We have to define the state of the population. The simplest Maximal description involves an infinite dimensional aspect, as we all know, which is a measure, not necessarily a probability measure, because probability means that the size of a population stays the same forever, which is a very restrictive assumption. So in general, not an infinitely many, not an infinite size of the population, so it's a bounded non-negative measure. I mean, but it's an infinite dimensional object, so except in very particular cases, we have to expect that the models are going to be infinite dimensional. And that's the so-called master equation. But in fact, it's the those are really the extended mean field equations as described in our work with Takis Ioannidis. Okay, so today I want to make a tiny little step in the analysis, in the global analysis of the master equation, taking into account that we can't expect global uniqueness and global smoothness. So what do we do? So there will be some wild speculations at the end of my lecture about that. And we are going to work out an example, which is joint work with Ben Seeger. And more details, or some other details can be found in the last lecture of my Collège de France course and this year, and it builds upon stuff I did on transport equation in that course. So introduction review, non-increasing solutions, that's going to be the very particular case. Maximal and minimal solutions, regularizations and classifications, attempt of a classification, and plus wild speculation. Brief review, I already mentioned why I consider that at least my focus, except for applications, which gives ideas about in which directions to go, my focus is clearly for some years has been on the master equation. Trying to accumulate facts with a question mark, global or complete analysis of master equation for extended mean-field games. So a word about the formulations. In the space of measures, as we did originally with Jean-Michel Lasry, and see my lectures, my old lectures at Collège de France, this invention of an Hilbertian formulation. And recently we worked out with Charles Bertucci a semi-Hilbertian formulation. So if the semi-Hilbertian and the one in the space of measures are completely equivalent, modulo natural regularity assumptions, there is a difference between the Hilbertian, which is much more a formulation, and the others, because it's much more compact. And so extracting the information to go back to the space of measures requires more work. And of course, I want to point out, but I guess he already gave this lecture about the weaker formulation in some cases in the space of measures, which are due to Charles Bertucci. As we all know, there are two particular cases. One which is not a particular case, it's just the situation of the master equation or the extended master equation in finite state space, and we have to deal with non-conservative hyperbolic systems. And I'll come back to that because I consider that this should be a direction in which a lot of analytical effort needs to be made. We also know that in some particular case where you have no common noise, or more generally with more complicated formulation, you can have a backward-forward formulations, which is certainly technically very useful, but in general shed no light on the global properties for the master equation. And this is due, think of by analogy of characteristics versus conservation laws and Hamilton-Jacobi equation. I'll come back to that because they could be useful in trying to achieve a more global understanding. As I already mentioned, and I want really to emphasize this today, that the interpretation through Nash equilibria and going to infinity is certainly natural and interesting, and I'm partly responsible for some of the activities in the direction, but it's limited. It doesn't extend to extended mean-field games, non-convex Hamiltonians, multi-level mean-field games, and so on. when I say it doesn't extend naturally, because with Nash equilibria, you can always find some, essentially any kind of equilibrium problem can be recast through a complicated and very often not natural way can be recast in terms of Nash equilibria. I gave a long time an example which shows that when looking at eigenfunctions of symmetric matrices, you can recast that at Nash equilibria. Almost everything can be recast as Nash equilibria. So I insist upon the natural in terms of modeling Nash equilibria. What about well-posedness? Well, those are almost all results locally in time. I did that a long time ago in my courses at Collège de France. A remark that experts know well, but it's not always well known, is that regularity implies uniqueness. But which regularity? This is an observation I made a long time ago. And recently with Charles, we tried to be as economical as possible. And we realized that, say, in the Hilbertian formulation, that the only thing you need is Lipschitz on the Hilbert space, okay? Which amounts to say in the measure space, in the formulation of space of measures, that the gradient with respect to the state variable, x, that the gradient is Lipschitz in xm. In fact, it's slightly more general than that, because that's the compactification. This is just a loose word. I'm using it, the word compactification loosely. That takes place in the inversion formulation. So Lipschitz in xm, so C11 in x, and the x derivative is Lipschitz in m. Lipschitz in m, well, if you think that you want to have arbitrary measures, it has to be the Monge-Notorowicz-Wasserstein matrix 1, which is a norm, which is W minus 1, 1. It's over the spaces norms, and which makes no difference between probability measures and arbitrary measures. We understood that the so-called monotone regime induces global smooth solutions, again in my courses, and our joint work with Pierre and Pierre and François Delange. But in general, so I should say, when I say monotone, I should really say monotone convex, because that's monotone for the value functions, but it's convex Hamiltonians, okay? In general, there is a tremendous non-uniqueness, and I'll come back with that. Non-uniqueness appears in finite time because singularities and singularities appear in finite time, time being the horizon. Constructions are very easy in the potential case. It was done a long time ago in my courses, and there has been since then many interesting works showing the ubiquity of non-uniqueness phenomena. Okay, global unique solutions, the potential case. Yeah, the potential case where you can reduce those equilibrium equations to a Hamilton-Jacobi-Bellman equation, also in general by using the concepts of viscosity solution of Hamilton-Jacobi equation. By the way, as a side remark, I said that we were probably mistaken in putting the name games in Minfield games, and certainly the word viscosity in viscosity solution was not right either. So I made two naming mistakes in my life, at least two. But anyway, this is how the terminology has been stabilized. So unique viscosity solution of Hamilton-Jacobi equation. But in some sense, it hides the fact that there could be other equilibria, because there is a selection principle which is involved. And other equilibria as weak solution of the Hamilton-Jacobi-Bellman equation is not the right concept, as I will come back later on. Of course, a technical remark is that the notion of monotonicity has many, many variants depending on the formulation, which type of monotonicity you're working with. But some form of monotonicity is a general recipe that we have for global uniqueness, which is a rare phenomenon. Beyond multiplicity, a question mark. Here is the extended mean field game without noise in the case of finite state space. It's this hyperbolic equation I don't want to comment. It's the same F for all components of the vector field U, which goes from Rk to Rk. State space, let's say, is Rk. I'm simplifying a little bit, but that's let's not worry. Fg, no restrictions like F being the gradient of a convex Hamiltonian. That's where extended plays a role. G of x and u. Okay, global solution if U naught is monotone and Gf is monotone. G is the right-hand side, F is the transport term in the first order operator. So Gf monotone R2K. But there is more. Clearly, if we take F equal U and G equals 0, then you have a global smooth solution if, and it's almost an if and only if, but not quite, if U naught is a composition of two monotone operators, okay? So what that means is really something about the spectrum of the Jacobian of U naught, but I don't have time to get into that. This was explained in my courses a long time ago. More generally, clearly you have global smooth solutions if you have a diffeomorphism that transform your problem into another problem which has these monotonicity properties. So these are something to do with the Poisson brackets of the vector fields, but that's big words, doesn't help. What about characterization? Unknown. Okay, so there is more, but not much more. And in particular, in the above example with noise, we don't know anything else but monotonicity. In fact, once again, the potential case is misleading because in the potential case, the analog of monotonicity becomes convexity, and it's basically a necessary and sufficient condition for the global smooth solution, convexity. And we just saw that the composition of two monotone operators gives a global smooth solutions. So there are less global smooth solutions in the potential case. Part of the reason is that assuming that you have gradients all over the place and that it's a potential case is a very restrictive assumption. In 1D, any vector field is a gradient of a gradient vector field. In 2D, that's a little less frequent, but as the dimension grows, roughly speaking, there are less and less gradient vector fields when you look at the entire space of vector fields. And in infinite dimensional, there are essentially exceptions. Okay, so we should keep this in mind. Doesn't mean that it's not interesting to look at those particular cases, but be careful. It may have zero implication on in the global picture. Strong noise regularization. I want to go back. I want to mention regularization because we will see the effect of various regularization. François Delarue had a very interesting study about strong noise regularization where singularities disappear, and I had a slightly, but not so different, presentation of that with another strong noise regularization, let's say in the inversion formulation. I'm just using these words because I'm going to come back at the very end about those regularization. So that's more or less what I know, and but I'm stubborn and I want to understand better what happens when you lose uniqueness. Okay, because in fact, mathematically, we are the analysis and PDEs has been so much influenced by physics. Then when a problem doesn't have a unique solution, there is something wrong with the model. We deduce that there is something wrong with the model. In this type of modeling, which involves large populations, it's completely different. You can't expect to have unique equilibria. That's also, by the way, also true with Nash equilibria. But in general, if you think about dynamical equilibria, there is no reason to think that you could have unique equilibria. So then the next question, which is interesting, is when does the non-uniqueness appears? We already saw that that's because of singularities. And the next question is, can we say something about the set of equilibria? Okay. Which, by the way, there is a word I didn't use, which is the time consistency of the models. And time consistency of the models are broken if you don't work more by any kind of backward-forward formulation. While it's transparent if you're interested in an evolution equation in infinite dimensional space or in the finite state space in RK. There is an obvious typo in the first equation, it's du over dt. So with Benziger, we became interested in a situation. In fact, we made a false proof to begin with, which means a proof that was false, considering it's more general than that, but let me simplify as much as I can. You already, you can see also that I simplified. It's more general than that, but I want to simplify as much as possible the presentation. So in the dynamics, in the first order transport term, it's f of u, and the right-hand side is g of x. You could have f of x and u, g of x and u. I don't want to deal with such straightforward extensions, but data which are f, g, u naught, assumed to be bounded to avoid any technicalities at infinity, are non-increasing as vector-valued functions from Rk to Rm. What that means is that each component is non-increasing, decreasing, with respect to each variable. Okay, it's a very strong assumption. I'm not claiming any generality. Just want to make this assumption and observe that the last sentence, that formally these properties propagates when g is non-increasing and f is non-decreasing. Well, economically, it's not crazy. I don't have time to go into that, but this is just as a mathematical example. So non-increasing. Well, first there are facts. When you take vector-valued functions from Rk into Rm, which are non-increasing in that sense, they are automatically almost everywhere continuous. And not only are they almost everywhere continuous, but they are almost everywhere differentiable. This is more or less known. It's an easy consequence of the so-called Stepanov results on the almost everywhere differentiability. I'm going to use always the lower semi-continuous representative, which is then right continuous. By right, I mean, of course, the positive ortant, and with left limit. So phi with the lower star is the upper semi-continuous envelope, which is just the left limit, which is, since it's now increasing, above phi of x. Now I have functions which are defined everywhere. As I said, let me formally non-increasing, this non-increasing feature propagates if g is non-increasing and the phi is non-decreasing. I'm sorry, and I mean non-increasing, second typo. And the proof, the formal proof is just you differentiate and look at the signs, be careful, and you see that you can never cross zero. That's as long as you stay negative, you have a negative differential inequality that reinforces the inequality. You never can cross zero. So when you're in one dimension and f is u and g is zero, what you have is the famous Burger's equation written in non-conservative form. And you all know that if u naught is decreasing and is not constant, if the initial condition is decreasing, then discontinuities always appear in finite time. It's not they appear sometimes, it's always. And then, of course, Burger's equation having a physical background, people have searched and found a criterion, which is the so-called entropic criteria, a criterion to select one solution, the good solution, in the sense that it's a limit of viscosity regularization. You just add to the right-hand side epsilon, second derivative of du. Okay, so that's a trivial, well-known example, but we know that we are going to face singularities always. If you notice smooth, say Lipschitz, there exists a unique Lipschitz solutions. That's a very particular case of what I said before. In the inversion, Lipschitz is the regularity you need, which, by the way, is not so. It's not so obvious that you can define solutions which are just Lipschitz. There is some work involved that I don't have time to detail now. So they are smooth and Lipschitz up to time to some critical time T naught. And not only you have smooth solutions, but you have a comparison principle, an ordering principle, which of course reflects the very stringent assumptions about being non-increasing. Okay, so that is this comparison principle, which is true until you reach the singularity. Of course, this equation, one more typo, there is no plus in the after b of x. Sorry for those 3 typos. A linear equation are indeed lurking behind du over dt plus bx gradient q. In some sense, things like a fixed point, you have once you have f of u, you have a certain b of x. And we all know that such transport equations are intimately connected to ODEs, x dot plus b of x equals 0 with an initial condition. Okay, so in fact, and that was explained in details in my course, in such a situation for ODEs, you have a maximal solution that solves exactly x dot plus plus b of x plus, and b is the highest value, is a minimal value at b, so that the it is assumed to be right continuous. It's and there is a minimal solution that solves exactly the equation with the left limit b star among all solutions of x dot plus b of x contains 0, where b is the ordered interval, order in our n, or m, I don't remember, b star b. Okay, so those are all the vectors which are in between. X plus and x minus are non-decreasing in x naught. And when you take the maximal solution and you take its lower semi-continuous envelope, which is in fact its left limit, you have x minus. Since the non-increasing functions are almost everywhere continuous, you deduce that for almost all initial conditions, you have a unique solution of the ODE, which is also the almost everywhere limit of regularized flow with an epsilon Brownian motion. In fact, it's even better than almost everywhere. In 1D, it's except on a countable set, and there is a natural conjecture, which is to say that it should be always except on a set of Hausdorff dimension -1 and -1. But that's technical, and we don't care. So what those facts allow, they allow to make a complete theory of the linear transport equation and of its dual equation, which is the conservative equation. So we understand in that very, very particular case, the structure, the mathematical structure of the transport equation. So what about the master equation in that, again, particular case? Well, for the nonlinear problem, you also have a maximal non-increasing solution and a minimal non-increasing solution. Well, what do we mean by solutions when they are not, let's say, continuous? Okay, because in general, they are just non-increasing, they can have jumps. Well, you can use 3 notions. One solution, which is the equations almost everywhere, using almost everywhere differentiability. You can have a viscosity notion, which is to say that whenever you take a maximum point, which is a maximum of all the indices, you have a differential inequality that you expect from the equation, and at a minimum point you have the other inequality. But then the question is, since u is not continuous, which values of u you choose in that inequality? Well, the less restrictive is certainly the lowest possible, f of u star, so that's the greatest generality, and while for the minimum you take f of u. So you have to choose a value, okay? So in some sense, for the sub-solution, you choose the minimum of all possible formulation, which is the usual discontinuous viscosity solutions relaxation, while for the super solution, you would take the maximal possible inequality. So, but you have a third notion, which is much more in the spirit of dynamical equilibria, which is to say that ui's solve the linear transportation with b equal f of u. I don't want to define what does that mean, solving the linear transport equation. This is a consequence of the of that simple theory on ODEs. And so in some sense, you solve linear transport equation and you want, you have a solution, see if you have a fixed point. So the above results holds for the two last notion, the maximal solution, the minimal solutions, etc. The above results holds for those two notions. Both notions imply the almost everywhere notion. I do not know if it holds for the almost everywhere formulation. I don't know. I suspect it is not true, which is a very strong indication that almost everywhere is not the right notion. Okay, which is a serious problem. Okay, so the proof follows a linear equation analysis with a systematic use of ad hoc regularizations like conditions with kernels, which are like regularization with kernels with conditions on their support in the positive or negative orthos, or if-sup convolution which pick points in the orthos. The 1D example shows that in general, the maximal and the minimal solutions are different. Take the Burger's equation, take something which is 1 if x is negative, 0 if x is positive, then the minimal solution is just the initial condition, doesn't move at all. So you have a jump discontinuity, which is decreasing a discontinuity at 0, jumping from 1 to 0. The solution stays the same forever. The maximal solutions go at the maximal possible speed, maximal value of the initial condition. That's 1, and you have a solution which is u naught of x minus t. So here we are. We are exactly in an example as predicted, singularities, and we have a compact set of solutions which are all in between a maximal one and a minimal one. In fact, when you do viscosity regularizations, examples show that you pick a third solution. And that's exactly the point that I want to make, is that you can create, I took the simplest possible regularizations, you can create all the solutions through various regularization. Here I'm taking a strange regularization, which is by adding a nonlinear term in the gradient. Gradient use epsilon square. This creates Lipschitz solutions automatically. It's not a trivial fact. That's something that we observed a long time ago with Mariko Arizawa. Never wrote this down, and this is completely general. So if you add this regularization, as epsilon goes to 0, you go to the max solution. If you add, you change the sign, as epsilon goes to 0, you go to the minimal solution. And in general, if you add a Laplacian, it doesn't converge to the minimal or the maximal. It converges to limit in between. In fact, if I go back to the example, which is this indicator function of x negative of Burger's equations, all the weak solutions in the two sense, not almost everywhere, not derivatives of weak solutions of Hamilton-Jacobi equations. With the two notions I mentioned, all the weak solutions, that's something that can be checked, are given by u naught of x minus c of t, where the only condition on the speed, c of t, is that c prime varies between 0 and 1. So that's a compact set of solutions, right? With some trivial topologies. It restores the whole set of solutions, restore time consistency in the sense that if you patch together in time two such weak solutions, take one up to some time t1, and then patch together in a continuous fashion with another choice of the speed, it is indeed a solution because you have c prime between 0 and 1 almost everywhere. So, and furthermore, in that case, for any such solution, there exists a nonlinear regularization whose smooth solution converges to that solutions. So they are all achievable, okay? This is the end of my example. And let me make some wild speculations, which at least I think the first step I'm going to add is precisely to understand, to try to understand much more what's going on in for those hyperbolic systems, which have a very specific nature because they all share the same transport term. So that's why I expect much more can be said. In particular, the method of characteristics applied to such systems. But anyway, so here is my, I don't want to call it conjecture, but my wild beliefs, dreams, is that, okay, most of the times we're going to lose uniqueness, fine, because we are going to have singularities in finite time. Then we have various solutions which are equilibria of interest, which can be obtained through various regularizations and possibly various modeling. And the modeling, in fact, I'm convinced, is incomplete. Because in some sense, you need to add some rules when you encounter the singularities. This is something that we experience in a very practical problem in oil production because of some kind of singular phenomenon. And for the numerical solution performed by Yves Jeux, we had to add some kind of arbitrage rules at grid points which were clearly going to the singularities. And then the numerics worked like a marvel. So I expect that we made some choice in those examples. Clearly here on this example, it's really about describing as time goes on, choosing C prime is choosing the value of U in the above formulation. 0, 1, something in between. So, and that's like something to say, well, okay, there is a singularity in the dynamics of the population. There is a choice between various equilibria. And somehow, if we want to choose one, if we want, we are not obliged to choose one, we have to add new rules, new models. How to get there mathematically, I have no clue, honestly. One option is to go numerically, trying to investigate what does it mean implementing new rule when one detects the singularities. Well, in order to have at least some recipes, which will then make perfect sense in terms of modeling, as I made in the oil production model we studied. Another way, which is vague in my mind, is indeed to use the whole characteristic flows, and somehow which is falls into the differential geometry realm of Lagrangian manifolds and all that jazz, And clearly, the solutions are projections on restriction in some sense, and the singularities corresponds to a folding in the manifold, and there are various ways to project. In fact, differential geometers like Viterbo built other solutions because of the different projections of, let's say, Hamilton-Jacobi equations, which are different from viscosity solutions, nevertheless creating time consistency, which is a semigroup property in the easiest case of Hamilton-Jacobi equation. So is it possible to understand a little bit more what are the possible selection mechanisms, or at least to classify them in order to understand a little bit better these type of additional rules? I'm beginning to believe we need if we want to go beyond singularities. I don't believe at all in the selection of one particular solution which would be more interesting than the others. This is not physics. This is something else. Okay, I warn you that I would conclude with some wild speculation based upon very little evidence. This very particular example, what we encountered in this oil production model, who knows? Certainly, I consider this to be a very exciting direction, and I hope that many will join me in my interest. Okay, I have no clue how am I doing on time. I'm still a little bit not in very good shape because of everything that happened to me in the last few weeks. But anyway, I'm going to stop there.
Thank you very much. You were a few minutes ahead of time, so we have plenty of time for questions.
Even better.
Thank you. Yes, I have one question about the last part that you discussed about the convergence when you have modification or regularization of the equation. So you spoke about the limits of the equation. Did you say something about the limits of the trajectories of the characteristics? So either when you use the first regularization or the noise, what do we know about the limits of the characteristics themselves?
Okay, this is something I need to check. It's a little bit difficult to formalize these in general for the Hamilton-Jacobi type regularization. But if we specify, if we restrict ourselves to the 1D simple example, indeed, characteristics do go to the right characteristics. So it's completely, those are consistent features. Characteristics precisely at that point are not uniquely defined, and you can select the characteristics that you want by various regularization, as you can select accordingly, and same with consistent choices. So my gut feeling is that that's a general feature, but more than this example, I don't know. Okay.
Thank you.
If there are any questions in the Zoom audience, you can either just unmute yourself or post in the chat, either way.
I have a question.
Go ahead, yes.
Yes. So talking about these regularizations, so if you somehow change the noise using to regularize, can you also achieve different solutions in the limit of small noise, or you really need to do non-linear?
Yeah, I understand very well your question. That's why there was a word which was non-linear regularization, in the sense that if it's just pure noise, replacing a Laplacian by another parabolic operator won't make any difference. But if you have some nonlinear interaction between solutions and the volatility, then it becomes a completely different ballgame. And this makes sense. To have an amount of noise which depends on the value function and so on. With very little value, you could expect to have lots of noise and so on. But that's a very good question. And thank you for allowing me to make this point precise.
I have one brief question, which is, I guess you mentioned these models beyond Nash equilibrium, beyond game theoretic considerations. Are these kinds of things like bounded rationality and what kind of equations they would give rise to? Are these documented?
Absolutely. No, I mean, we have a collection of examples, but there is nothing written about that. Bounded rationality is an example. Another case is a worst case strategy. Each agent selects a strategy by a min-max because of unknowns, noise, and so on. Another example are multi-level. A population above another population, each influencing the other, and there if you take companies, large companies, or if you take financial markets, this is a very natural framework, etc., etc. So they are, again, I'm not obsessed about things being Nash equilibria or not Nash equilibria, because as I said, I don't know any example of something which cannot be thought as a Nash equilibrium. So what I mean is that really, from an economical point of view, from a behavioral point of view, Nash equilibria are not natural. Okay, that's point number one. Point number two is about bounded rationality. People are trying to, in economics, there is a huge literature about limited or bounded rationality. And this is a very complex situation. There are models I like very much, which lead to incredibly difficult analysis questions, which is to say that bounded rationality may come from the coexistence of two horizons in a decision process. A small time horizon and a longer time horizon. And that some sense there is an exchange of influences between those two horizons. Very interesting papers in that direction. And in some sense, the simplest possible case is when the horizon, the small time horizon, is instantaneous. So it's like having to choose between a rational anticipation and some kind of instinctive, immediate, myopic response. And the way this mixture is made doesn't need, and there is no reason to believe it should be convex, etc., etc. So there are many, many examples. Unfortunately, nothing is written, although the oil production model is flirting with non-convexity all over the place. So already having a look at singularities and so on, having a look at this oil production paper, which can be found in archives or AL, I don't remember. It's a joint paper with a bunch of authors. Let me try to make them in alphabetical order. Yves Jeux, Jean-Michel Lasserie, and I, and also, sorry, alphabetical order, Charles Bertucci after Yves Jeux. There is also, okay, Jean-Michel Lasserie, myself, Rostand, not Edmond Rostand, but whatever, and José Schenkman, famous economist. Rostand is the head of, is a CEO of a startup which is doing data on oil production and oil storage. Well, because of the fact that there are many populations, you have some non-convexity features that appear, and the notion of Nash equilibria, especially because there are some arbitrage advantages on the OPEC, which is a main oil producer, is rather complicated. Doesn't mean it's impossible, but it's not natural. So it's both a case where you have non-convexity or some kind of non-convexity. It's not entirely true what I'm saying, but you have some effective non-convexity. and singularities, and it's not clear that Nash equilibria make any sense. Maybe they do, but that in some sense, for many models, it becomes irrelevant. Well, I'm not saying it's not interesting. I'm just saying that it's not the objective of the model. That's where we stand. But we're going to see more and more cases.
Okay, thank you. Any final questions for Pierre-Louis? And let's thank him again.